Hey everybody, let's get right into enzymes and different factors that influence enzymatic activities. So, hopefully, you've heard this in previous biology classes, but enzymes work under optimal conditions best. Optimal means the best conditions for work. And so, just like everyone, we all work best under the perfect conditions. You don't want it too hot, too cold. You don't want to feel gross. You want to feel healthy, not too thirsty, not hungry. Then you're going to work most effectively, correct? Enzymes have very narrow ranges for where they work. So an enzyme might work most effectively at, say, 37 degrees Celsius. And what that means is it's going to work really good at our body temperature. If we change that temperature, we go down or we go up, the enzyme may not work as effectively. So here it might, if we go down to 30 degrees, the enzyme is probably going to decrease in its activity. If we go up to say 40 degrees or 42 degrees, then the enzyme's going to eventually stop working. It'll denature. So too hot of temperatures causes denaturation. Too cold of temperatures makes enzymes very, very rigid, and then they don't function as effectively. And so that's what it means to work perfectly or best at the optimum conditions for temperature. Enzymes also work best at an optimum pH. Most enzymes work at that neutral pH, anywhere between like 6 and 8 is going to be where they're going to work really well. So 7 would be like one of the optimal conditions. Anything below that is going to likely is acidic and is going to start decreasing enzyme activity. Anything high above that is also going to start denaturing those enzymes. So they work very effectively at a more neutral pH, but not all enzymes do. There are enzymes in your stomach that work in a very low pH. So think of pepsinogen is an enzyme that works in the stomach, and it works at a pH of between 1 and 3. Whereas we have salivary amylase in our mouth that works at a pH of more like a 7. If salivary amylase goes into the stomach, which it does, it gets inactivated. When pepsin moves into the small intestines, it becomes inactive. And then different enzymes work. This works in all organisms. So enzymes in bacteria are also going to have optimum pH and optimum temperatures that they work at. Enzymes have to be regulated. So we have certain metabolic pathways that are constantly running, but we have a lot of metabolic pathways that don't need to run all the time. So an example would be the enzyme for lactose that breaks lactose down isn't going to work all the time if we don't have lactose in our system. Makes sense? We utilize other enzymes so we don't have to produce those enzymes. So there's a thing called allosteric regulation that helps us in stopping enzymes from doing things when we don't need them. When you think of allosteric regulation, think of producing molecules that we don't need. So say we have over here some precursor, right? I'm sorry. That is going to eventually become some amino acid, right? That we are producing. If we have a lot of the amino acid, so we have lots of little amino acids over here, we don't need any more, then we would stop this pathway from running because we don't need this pathway. Allosteric regulation allows us to do that. So enzymes have their active site. Oh, I'm so sorry. That's not right. Just Erase that. Enzymes have their active site where the substrate binds, but they also have this allosteric site where another molecule can bind. And typically this other molecule is going to be one of the intermediates. So it might be intermediate A or B that's going to move in and bind so that we don't produce any more end product because we don't need that end product anymore. Sometimes it's the end product itself that binds to say, hey, stop running this pathway until we no longer have the products. When these are being used and they go away, then this material will come out and we can run this pathway again. That's allosteric regulation. Enzyme inhibition occurs through either allosteric inhibition, that's non-competitive inhibition, or competitive inhibition. So competitive inhibitors bind to the active site, and they keep substrates from being able to bind to those sites. So here's an example. Bacteria have to be able to utilize PABA in different metabolic pathways. So sulfa drugs are similar to PABA, are similar enough in structure to PABA that they can bind, and when they bind, then PABA no longer can bind. And then the metabolic reaction that it uses PABA is not going to be able to occur. And the non-competitive inhibitors are going to bind to the allosteric region, and they stop the ability of the enzyme from binding. So in non-competitive inhibition, which I think I like this picture best, it changes the shape of the active site, and then the substrate can no longer bind. So we have non-competitive inhibition that is used in regulating metabolic pathways, and sometimes we have different molecules that bind, and when they bind, then enzymes no longer can function and that pathway is inhibited, and it could be because it's a certain type of drug that's being utilized to kill off the bacteria. All right, I'm going to stop here, and we're going to get into the glycolytic pathway in our next video. Bye.